Thank you for having me. I'm Kameswara Mantha. Most of you know me. I'm a graduate student, finishing PhD student with Dan McIntosh at the University of Missouri, Kansas City. And in today's talk, I'm going to focus on some of my ongoing work towards my PhD thesis, which heavily involves something called as the closed pairs and tidal features, which are observational way of identifying galaxy mergers. So my thesis is heavily focused on understanding galaxy mergers and their role in galaxy evolution. So this work is being done in collaboration with Rachel Somerville and Peter Baruzzi and all of the following collaborators in conjunction with the CANDELS team. So let me go ahead, and I just want to say that my primary research interest is to understand the role of galaxy evolution in the grand context of galaxy evolution. This is a common picture put forward by many studies in the theory and as well as empirical studies, where connecting galaxy mergers with the grand scheme of morphological transformation and transformation of the physical properties of the galaxies themselves, where galaxy mergers are thought to transform galaxies both in morphology, physical properties, and etc. From being alive in star formation and to red and dead and elliptical in shape. So I want to understand the importance of galaxy mergers in this whole picture. So there are two key steps in understanding the connection between galaxy merger and galaxy evolution, one of which is identifying galaxy mergers. And that will be the main focus of this talk. And robustly identifying galaxy mergers, I think, is more important. And the second important thing is to quantify the importance or the rate at which galaxies merge and its evolution as a function of cosmic time. So those are the two key aspects that I focus on in my thesis. For the purpose of this talk, I'm going to focus on the first one. Now, let me dive into some of the frequently used empirical ways of identifying galaxy mergers. So there are primarily two ways of identifying it. One of the famous one is the closed pair method, where galaxies in close plausible physical proximity are identified as future or ongoing merging systems. The other way of doing it is to identify hallmark tidal signatures due to tidal forces during merging process as an indicator of ongoing merging activity. So again, for the purpose of this talk, I'm going to focus on the closed pair method and some of my ongoing work using particular to this method in the context, okay? So just a very quick refresher. Closed pair method is basically trying to select galaxies or a mass selected sample of galaxies that host a major or similar mass companion in projected proximity within a certain radius, let's say 50 kiloparsec, and also satisfying a physical proximity selection, either it be a spectroscopic velocity difference or a photometric redshift based selection cut, depending on the kind of data at hand. If we have spectroscopic data, studies use a spectroscopic velocity difference. If not, they'll usually refer to photometric redshift based selections. And the primary quantity that everyone quantifies is the pair fraction, defined as the fraction of massive galaxies in the sample that host a major companion, satisfying some selection cut that is defined above. And those are the common selection criteria used in the literature. So I'm just giving that as an example. Now, what's the primary issue? So there are several challenges at hand in this current method. And one of which is that even if we account for obvious changes in the pair selection functions, several studies often disagree in terms of what the pair fraction is at a fixed redshift. So there's a large variation in the empirical measurement of pair fractions, and that scatter is hard to understand. So one of the things that should be accounted for is the role of observational effects such as photometric redshifts, photometric redshift errors, stellar mass errors, detection completeness, and field-to-field variations depending on the size of the field you're using to quantify the pair fraction. So these are all plausible contributors to the observed variations from different studies. So I think this is an important quantity that we should systematically understand and possibly calibrate to derive better pair fractions. So for this purpose, I'm using SantaCruz semi-analytic model-based model mock Lightcones by Rachel Somerville et al. And collaborators. Briefly, SAMs use the dark matter merger trees and use semi-analytic prescriptions for the baryonic physics and forward model them to populate the dark matter halos with galaxies. And then they are projected onto a celestial footprint, such as the candles here. And we have a mock Lightcone observation of like the candles-like celestial footprint populated with the galaxies from the SAMs. So we are using this particular data set, and we are additionally incorporating observational effects to in fact understand their role. We are incorporating effects that mimic statistically mimic the properties of candles data. So the first thing that we do is incorporate photometric redshifts and errors. For this purpose, I'm using the candles spec-z and photometric redshift compilation by Titan et al., who also did a Bayesian analysis to quantify the point estimates for photometric redshifts and also corresponding errors. So in this plot, I'm showing the candles photometric redshift error distribution as a function of h-band magnitude on the x-axis. And what I do is I assign a photometric redshift error for each galaxy in the SAM, and then I resample a photometric redshift from the PDF centered at the true redshift of the galaxy and the uncertainty that we just assigned for the SAM's galaxies using the candles statistical distribution. On the right hand side, I'm showing the difference between the true redshift in the SAMs for each galaxy versus the photometric redshift I assign as a function of photometric redshift. And you can see that we are statistically mimicking, the punchline is we are statistically mimicking the photometric redshift properties of candles galaxies in the SAMs. Similarly, I'm also incorporating stellar mass systematic and random uncertainties using a log normal Gaussian distribution prescription by Peter Beruzzi in 2019. And in this plot, I'm showing the difference between the true stellar masses versus the observed stellar masses that we assign based on resampling the PDF centered around the true redshift and the error prescribed by Peter Beruzzi et al. In this plot, basically, I want to visualize that we are mimicking the stellar mass and systematic and random uncertainties to our SAM's galaxies. Another point that we are also incorporating is detection completeness or incompleteness, in fact. So for this purpose, we are using the latest completeness functions derived by Duncan et al. In the candles fields for different depths. In this left-hand side plot, I'm showing the detection completeness as a function of h-band magnitude from Duncan et al. And then I approximated their selection function, the completeness functions using a analytical prescription. And using that, I incorporate these as a probabilities for each galaxy in the SAMs. And on the right-hand side plot, I'm showing what happens when we incorporate this. On the y-axis of the right-hand side plot, I'm showing the fraction of galaxies that have a completeness probability greater than 0.9 or 90% in bins of stellar mass as a function of redshift. So the punchline is that, at high redshifts, you're potentially missing some major companion galaxies that would be major companions to the massive galaxies that you select. For example, you can see the red line there, or dashed or solid line. At least 10% of the galaxies at high redshift will be missed for your massive galaxies that you're looking at. So you might be underestimating the pair fraction in that sense. So we want to quantify what happens if we incorporate the detection completeness into this. So after incorporating all these effects, I started to quantify the pair fractions by systematically switching one thing off versus one selection effect on and off and so on. So first of all, before we dive into what happens if we incorporate observational effects, I am showing the pair fraction evolution as a function of redshift without incorporating any observational effects. So this is like, if I have the SAM mock Lightcone, all the true information for the galaxies, this is what the pair fraction evolution looks like as a function of redshift. And very briefly, the pair fraction evolves mildly with power law of 1.5 slope. You can see I plotted this for two different projective proximity selections, which are common in the literature, just to show the variation, what happens if you choose a restrictive versus a less restrictive selection cut. And this is expected because if you use a larger annulus for your pair selection, you are selecting more pairs. So this systematic offset is expected. Now let's dive into what happens if we incorporate the observed values. For example, in this plot, I'm showing the pair fraction evolution if I incorporate the photometric redshift and the stellar mass uncertainties into the picture. So on the left-hand side plot, you see the pair fraction, and the red solid line is the same line that I showed in the previous figure when you don't incorporate any observational effects. And when you incorporate observational effects, you see two different lines there. One is in olive and the other one is in cyan. For two different redshift proximity selections in the literature, the olive green line corresponds to Kevin Bundy's 2009 selection criteria, which uses the photometric redshift uncertainties of both the host and companion galaxies, whereas the cyan line is by Greg Snyder in 2017 in his illustrious closed pairs paper. On the right-hand side plot, I'm illustrating what's the effect of incorporating such photometric redshift selections into pair selection functions. On the y-axis, I'm showing the value, the quantity W prox, which is basically the fraction of galaxies selected based on your photometric redshift selection that have a small velocity less than 500 kilometers per second. So basically the punchline of that right-hand side plot is that 35% of the pairs selected based on photometric redshift proximity cuts have small velocities, i.e. Less than 500 kilometers per second, which is usually used as a good selection cut in the low redshift studies to select plausibly physically bound pairs. So this is interesting in terms of that. Let me move forward and then try to understand what is the effect of stellar mass errors in selecting major pairs. Since we are using stellar mass uncertainties, the uncertainties on the stellar mass will scatter the host and companion galaxies in and out of this major pair selection window. So I want to understand what is the role of this. So on the left-hand side plot, I'm showing the ratio, the mass ratio, when you use the true quantities in the SAMs versus the observed quantities with the stellar mass uncertainties incorporated. So you can see there are objects that are scattering in and out of that window. So I wanted to quantify this effect. And I'm using the quantity W major, which is defined by that equation there, where lambda and kappa are ratios of true positives with true positives and false positives and false negatives incorporated simultaneously. So this is identical to something called as the F measure in the literature. So I'm basically using that prescription. And then I'm plotting the F measure as a function of redshift for different selection criteria. But the overall punchline is that when we incorporate stellar mass errors, 85% of the ones that we select using observed values are actually true pairs, according to this plot. And this evolves with redshift and falls to around 65%. This is an interesting thing that we have noticed, which should be incorporated. So the next thing that we did is quantify what happens if you incorporate detection incompleteness into the picture. So on the y-axis of this plot, I'm showing the W incomp, which is the ratio of the pair fractions with the detection incompleteness incorporated. And the denominator is what if you don't incorporate the detection incompleteness as a function of redshift and something called as the H80. So H80 is the 80% detection completeness survey threshold. So I'm quantifying this W incomp as a function of survey detection limit. So in principle, if you have a survey and if you want to apply a correction factor, you could basically read off this plot and try to correct for it. So the punchline from this plot, just simply saying, and the dashed dark blue line corresponds to the candles wide depth, 80% survey limit. And basically 10 to 20% correction is required for the pair fractions at the highest redshifts. The different colors correspond to different redshift bins. So for example, the red line is at redshift of 3. So, approximately 20% correction needs to be employed for your pair fractions that you quantify without, to account for the incompleteness. One additional thing that I think is important is to quantify the effect of field-to-field variations in the pair fractions. So one thing that I did not emphasize enough in the beginning of the talk was that these the SAM light cones are have a celestial footprint that is larger than the native candle size fields. So we could basically slice the fields into candles sized native and try to quantify what would happen if you took different candle sized fields across the whole like footprint, and then quantify the variation in the pair fractions. So on the y-axis of this plot, I'm showing the pair fraction variation, the sigma standard deviation of the variations in the pair fraction distribution as a function of redshift. When you don't incorporate any observational effects in red line, and the remaining two lines are when you incorporate observational effects into the picture. So you can see basically that if you incorporate observational effects are actually impacting the field-to-field variations. That's one thing that I noticed. The second thing is that the main sort of just by eye takeaway is that approximately 1% to 1.5% pair fraction variation should be accounted when you're as an error bar. Let's say if your pair fraction is 10%, 1.5% should be the error bar on it just from the field to field variation for the candle sized field. So you could repeat this exercise for your favorite field of choice to see if it's a large effect or a small effect. So this is one thing that I did. Now the obvious next step for me to do is I derived all these calibrations. It would be really nice if I applied them to real data and see what the calibrated pair fractions tell me. So this is preliminary, and I have basically analyzed the candles data with a different selection cut than my 2018 paper, and then incorporated the W major, which is the major pair selection correction, the redshift proximity correction wherever required, and then the denominator's incompleteness correction. And so the solid blue points corresponds to no correction. If I just took the data and then I quantified the pair fraction for the given selection cut, and the open data points correspond to if I incorporate the incompleteness, major pair selection criterion correction, and also adding in quadrature the field-to-field variation error bars. And one interesting thing that we can also do is, since we don't have like large spectroscopic surveys across the whole candles fields to select pairs that have like small velocity differences, we could also, just using the corrections that we derived, we could infer the evolution of spectroscopically paired galaxies out to high redshift using this, I think. And the red points correspond to like that actually. So pair fraction for delta V less than 500 kilometers per second. So this is the current state of my analysis, and this is a preliminary result that we got for this candles reanalysis. So I'm going to work on this a little bit more and then write it up basically. Okay. For this is the first part of my talk, and then I'm just going to briefly go into simultaneous work that I'm doing using tidal features. So we are analyzing tidal features, and we want to understand how tidal features are detected, like the detectability of tidal features, and how often do we see tidal features among merging galaxies, like the time scale and so on and so forth. So these are also simultaneously important questions that we are trying to answer towards robustly identifying galaxy mergers. So again, the key challenges in doing so is the detectability of tidal features and the observability time, defined as how long do you actually see tidal features when you are following galaxy mergers. And then I think an important thing is to map the observed features to the physical properties of what caused them. So I think that's a really interesting thing to do. So in this example, I'm showing an example merger from the Vela zoom-in simulations from my 2019 paper. And then overlaid on top of it is the extracted features using my 2019 residual feature extraction method. So we developed this way of extracting features around emerging galaxies and quantify the surface brightness and possibly even additional quantitative metrics about the features themselves. So what I'm doing is I'm using the synthetic HST observations of major mergers in the Horizon AGN simulation. Roughly there are 7,000 major mergers for masses greater than 10 to the 10 solar masses, spanning redshifts 0.5 to redshift of 3, which is the ideal redshift range that I'm working on. So this is really interesting to do the same kind of analysis on tidal features within the same redshift range as my close pairs. And each merger is saved at 10 to high time resolution, 10 to 20 million years in time resolution, and at 3 different orientations. So it would be really interesting to follow these mergers and then quantify the tidal features and then try to understand several properties about it. So in the example, in the bottom panel, I'm showing example post-merger stages of galaxies, 4 different examples. And you can clearly see, like by eye, the visual tidal features there. So we want to analyze a specific time step after the coalescence to like understand what suite of features do these mergers exhibit, and could we like understand the detectability of them, how long do we see them, etc. So we just started to do this analysis, and we revamped our feature extraction to work with the Horizon AGN dataset. And in this example, I'm showing the feature extraction for a couple of snapshots for the post mergers in the Horizon AGN simulation. And we can quantify the surface brightness of it. So the goal of this work would be to use some machine learning and unsupervised learning algorithms to basically group features according to some properties and correlate them with the known properties of the mergers that cause them. For example, mass ratio, stellar mass of the galaxy, redshift, and so on, and understand the mapping between the features that we see and what caused them. So basically, there are 3 key takeaways to my presentation. I'm using the semi-analytic model Lightcones to understand the role of observational effects in quantifying the pair fractions, and I'm deriving calibrations for it so that you could apply to empirical data to derive calibrated pair fractions. And then the second thing is that we are using the Horizon AGN dataset to quantify the detectability of tidal features and understand the time scales on which we can see them, and then connecting them to the physical properties of progenitors that cause them. Thank you very much. If you have any questions, I'm happy to take them.
Thank you. This was a wonderful talk.
Nice picture too.
Thank you. Yeah, I just took it at 3 a.m. today. So.
Awesome.
That's really cool.
Awesome. Questions?
I have one. This is Chris Constantly.
Hi, Chris. Yeah.
Hi. How you doing? Very nice talk. Thank you very much. So my question is about the errors on the stellar masses. How do you actually obtain those? How are you measuring them? Because they're not as simple as photometric redshifts, sort of.
So Peter Beruzzi, in his universe machine paper, used observational data to constrain these 2 parameters on how the systematic and the random uncertainties on stellar masses evolve in a redshift dependent way. I'm basically using his prescription and then mimicking that prescription onto my data set.
And what I don't know Peter's work on this. What is the general error on the stellar masses that you're finding based on that method? Like how many Dec and stuff?
So I think it's around. So I should also mention it's capped at 0.3 Decs at high redshifts, but within the redshift range that we are talking about, it's usually on the order of 0.3 Decs as you go to high redshifts. But as you go like at redshift of 1, it's less than that. It's like 0.2 or 0.15 Decs if I remember correctly. But I can get back to you with the exact numbers if you.
Yeah, sure. One thing I would worry a little bit about. I don't know how Peter is doing this, but in general, stellar masses, I'm not sure that the errors get worse as you go to higher redshifts, unless you're really at the faint limit where your signal to noise is lower in terms of, say, the models you're fitting to or the measurements themselves. But if it's a magnitude issue, I could understand that. Thank you.
I'll send you an email with these specifics. Yeah, and we can discuss them.
So that NM, can you describe this plot a little bit more, like true and observed? Mm-hmm. So it's all simulated, right?
Right. So in the SAMs, they come with a true redshift with them. Now what I do is I get an error prescription from the Beruzzi et al. So we get a systematic meaning the offset that we need to do. And then we get an error bar, like a standard deviation on a log normal Gaussian. So we center it at the true stellar mass of the galaxy with the sigma, and then resample that distribution to derive like an observed stellar mass and assign an observed stellar mass from that.
So
And
you did this for all of the galaxies in the SAMs that span this quote true mass range, right? And then for these for redshift less than 1, because your error bars are pretty, but these are 1 dec. Those are smaller than 0.3, like they're like 0.1, right?
Right. So that's what I was saying. It's a redshift dependent thing. So the scatter itself is a redshift dependent thing, and it's capped at 0.3 decs at high redshift. So as you go, but like Chris said, they need not necessarily increase. So let me get back to both of you in terms of like showing. I have additional plots that show the behavior of the error as a function of redshift, and we can discuss it further there.
Yeah, it would also be useful to compare that against what we actually find with the CANDELS galaxies.
Yeah. Yes. Definitely.
I think what Peter's doing here is saying, you know, if all the other assumptions of my reconstruction of stellar mass star formation, evolving stellar mass star formation rates using all these continuity equations, if everything else is correct, then I need this scatter to match the mass functions at every redshift, right? So that's the sense in which it's sort of a post facto estimate of what the mass errors have to be if everything else in his reconstruction is right.
Right. Take your hair.
Thank you.
Are there any other questions?
Yeah, just to follow up on maybe for Harry on how Peter inserts those errors. Does he just basically add an error kind of by fiat, or does he actually drive that error on some intrinsic distribution that has some scatter?
I don't remember. I mean, I'm pretty sure it's a analytical distribution, but I don't remember what he's assuming.
Because I'm thinking if there's some internal variable that drives a scatter, then we could try and look for that in the data.
Yeah.
Like if it's age or reddening or something.
Can you go to the completeness plot again? Because that went by just fast, and it was, let's see, there was that one, and then there was another one, right, as well?
So this is me applying the completeness functions onto the data. So, and then I'm showing what happens if you do that on the right-hand side plot. So, so were you wanting to look at this, or maybe?
It was a function,
This one, yeah.
Yeah.
So, yeah, it's, I guess I was scratching my head about whether it's going backwards.
So yeah, so no, so the x-axis, this is a confusion I've encountered multiple times. I'm happy if there are any suggestions in terms of changing the x-axis to something that's less confusing in the first go itself. Please let me know. This is still in the making, so I can obviously change it if it makes it clear. So the x-axis on the towards the right-hand side would be you have a deeper depth. So that's why. So you can see like, and then the left-hand side, if you go to the left-hand side, 80% completeness that is brighter means you have a shallower field. So
okay, so it's the horizontal axis would be for a different set of observations.
Right, exactly. Yeah. Okay. So for example, if I have a hypothetical field, and then I know that 80% completeness limit is like, 25, and I quantified my pair fractions, and I wanted to correct for the fact that there's incompleteness. So that you can read off that x-axis, and then at a specific redshift, you can make a correction like, okay, half are missing. So
yeah, okay, makes sense.
Yeah.
But this isn't, to be clear, these are your pairs that are defined in a very particular way, right? Major and certain mass limit.
Yeah.
So which selection is this? The 50, the 30 kpc?
So the fiducial selection throughout my analysis is 5 to 50 kpc. Mass ratios less than 4:1. stellar mass above 10 to the 10. So I don't
The
change
primary or the total?
the primary, yes.
Okay. And then this redshift selection.
And then the redshift proximity selection, yes. So I'm in this talk, I'm just showing one plot for this, but I actually do this for 3 different redshift selections as well. So I show them side by side. But for the purpose of explanation, I think this is the best.
So I had a question that the punchline plot for the SAM analysis I put in the chat.
Yeah.
Was your last slide, that one. Yeah. So basically, what I'm taking away is that if you actually correct your observed pair fractions using your prescriptions, you get about a factor of 3 lower fraction.
Yes, the bulk of this effect is coming from the major pair selection being impacted by the mass errors. The mass errors are scattering, at least if we
That's the biggest effect, because I thought the biggest effect was the fact that most of your pairs selected on a photo Z are not actually less than 500 kilometers per second.
So you need to make, so in this plot, you can make 2 comparisons. So I'm actually making a comparison between the solid blue points and the open blue points. I think you're making a selection between, comparison between blue points and the red points.
Right.
So that comparison is fine. And there, in that sense, in that case, the major contribution is coming from the redshift proximity correction. But if you take it out, we are using that as a tool to infer what the spectroscopic pair fraction evolution would be. So I don't know if it would be 100% appropriate to directly compare both of them together. But a more appropriate comparison would be to actually look at the difference between the blue point, the solid blue points and the open blue points. And in that case, the major contribution is from the stellar mass errors scattering the major pairs in and out of the window.
Okay.
So I think we are close to the time for the talk. So if people have any more questions, I would definitely encourage them to either post on the